I want to review what we know about magnetism. We've learned a number of things over the last few days and watched some other guys' videos. Well, I want you to watch mine now. So this will serve as a good review before we have our test here in a few days, sometime next week. Magnets. Well, there's two ways to make a magnetic field. Way number one is listed here first. Moving electric charges make magnets, and those are called electromagnets. If I have a pile of protons sitting here and they're just sitting here, there is no magnetism. But if they are moving, then there is magnetism. Same thing with if I had a pile of electrons. It's the fact that they are moving that makes them make a magnetic field. Electricity has to be moving for it to make a magnetic field. Well, we have a special word for electricity moving, electrons moving down the line, or for that matter, a pile of protons moving down the line or pretending to move down the line. We call that current. So whenever there is a current, there is a magnetic field. That's one way to make magnets. The other way is to use permanent magnets. Permanent magnets have internal electric currents called eddy currents. They are magnetized all the time. This is my cow magnet that I've been using for the last few days. It has a north end and a south end. It's not marked on this one, so I don't know which is which, but we've got these little field lines coming out. Inside of this, there's what we call eddy currents, these little currents of electrons just flowing from atom to atom, kind of minding their own business. And in a permanent magnet, we've aligned all those little currents up so that internally there is a net electric current, and it is that net electric current that causes this to be a permanent magnet. So that's the two ways you can get magnetism. Make it using electricity, or you use electricity, but it's kind of in a different form to make a permanent magnet. The metals that these must be made of are iron, cobalt, or nickel. Now there is some rare earth magnets made of niobium and a few other things, but most every magnet you see will be made of iron, nickel, or cobalt. Okay, now what happens when we marry these two things? Well, something magical happens, as a matter of fact. Ignore that noise, nothing just fell over. If I have electricity, I can make magnetism. We saw that here. I had electricity and it made magnetism. It made an electromagnet. Now when I turn this off, it goes away. The magnetism does. And we saw that magnets could make electricity. I don't think I can get this on the screen, but you remember this little demo where we took the magnet and we passed it through here, and I don't know if you can see the needle wiggling, but the needle's wiggling. By moving the magnetic field, I'm changing the number of magnetic field lines that are going in this coil of wire, I can actually make some electricity. So I can use electricity to make magnets and magnets to make electricity. And that's all well and good, but then when I take some electricity and a permanent magnet, I can do even more cool things. As a matter of fact, when I have electricity, a permanent magnet, and some type of motion, if I have two of these three, electric, permanent magnet, and motion, then I can generate the other one. Let me give you a couple of examples of that. I circled these because I was too lazy to write them all out. Motion and a permanent magnet, you can get electricity. A good example is a hydroelectric dam. It uses the motion of the water to turn a coil of wire that is near some really, really big magnetic fields, really big permanent magnets. And in doing that, you get electricity. That electricity runs the lights in your house. Another good example, some of you guys said you owned flashlights that had a little coil of wire in it that was weighted. You could move it back and forth, and the coil would move back and forth, and it would make the light. You were taking motion, adding to it a permanent magnet. The coil of wire was going back and forth through the magnet, and from that it was able to make electricity. Second example, if you have electricity and motion, you can make a permanent magnet. We just showed an electromagnet. Now, admittedly, when I turn my electricity off, the magnetism goes away, but I can turn this on, and I can then take a needle or something and drag it across here and magnetize the needle, and the needle will stay magnetized. That's how they make compasses. As a matter of fact, the little needles inside have been permanently magnetized by an electromagnet. And then the last example, if I have a permanent magnet and electricity, I can make motion, and that is a motor. We've seen several of them in class, very, very simple ones, but the moral of the story is if you have two of those things, electricity, permanent magnets, and motion. If you have two of them, you can get the other one. And there are so many adaptations of that in our life. We see those technologies all over the place, and I've showed you 8 or 10 of them already. Okay, now the one that's giving all y'all trouble, the right-hand rule. There are two right-hand rules. We'll edit that noise out. There are two right-hand rules. The first one involves a current in a wire. There's nothing else exists except a wire, and it's got some electricity going down it. If that's the case, it's going to make a magnetic field. That magnetic field is going to be circular around the wire, and my right hand, curled like that, tells me how the magnetic field looks. I align my thumb with the current, and that would be conventional current, by the way, and my fingers curl in the direction that the magnetic field is going. So if I have a wire coming from me to you, out of the screen, the current is coming towards you, and again, that's conventional current, then the magnetic field, the circle of magnetic field around it, is shaped like that way. This is the point of the arrow, so right here, it's pointing that way. If I had two wires, then they would both be pointing in the same direction, and because of that, they would be attracted. That is, you would have the front, for one wire, you'd have the front of the points of the magnetic field here. The other one, you would have the back of them near the front of the other one. That would be like a north and a south pole together, and they pull together. If, on the other hand, I had one wire with current coming toward you and one wire with current coming back this way, they would repel each other. And that's a phenomenon we can demonstrate, maybe not in classroom, but we use that technology in fancy machines all the time. So that is when there is just a wire and it creates a magnetic field. But if I have a wire carrying current and it creates a magnetic field, and I happen to have that wire near some permanent magnets, then the magnetic field from the permanent magnets and the magnetic field from the current interact and either attract or repel, and we've developed a second right-hand rule to explain that one. That one looks like this. Physics gang sign right there, everybody. This we use only if there's current and a permanent magnet. This finger points in the direction of conventional current. Middle finger points in the direction of the magnetic field from the external magnet, which always runs from north to south. And my thumb is always perpendicular to these two vectors, current and magnetism. And my thumb points in the direction of the force. So let's kind of work through some problems with that. If I just have a wire, here's a picture of a wire that is, the current is going into the board. So I push my thumb like that, and you'll see I drew a little vector there that shows which way the magnetic field lines are going. Same thing, I have one coming out of the board. I'm sorry, I got confused there just for a second. Coming out of the board, so it's pointing towards you, and the curls go the other way. Okay, down here, and you can just barely see it, but I've got magnetic fields drawn from right to left across the screen, and I've got a current going in. Well, I take my finger and I point it in the direction of the current. I take my second finger, that was my index finger pointing at the current, take my second finger and point it in the direction of the magnetic field by the external magnet, and then my thumb points up. It points perpendicular to these two, which would mean this wire would feel a force that would make it jump up, rise up. So we're going to practice some more of that in class. I realize that is somewhat confusing. And lastly, let's talk about the formulas. There are really only two formulas that we're going to use with this phenomenon. If I have a current going down a wire, and it is in a magnetic field rather, then it's going to feel this amount of force. The magnetic force is equal to the current, I, times the length of wire, how much wire is inside the magnetic field, times B, so that I never have to say this again in class. B is the variable that we use for magnetic field. It is measured in Tesla, and the unit is 1 Tesla is equal to 1 Newton of force divided by 1 amp of current, also divided by 1 meter. 1 Newton over 1 amp times 1 meter. 1 amp times 1 meter is the denominator. Don't ask me that again in class. Now, if I have a current going down a wire, that's the formula I use. let's say I just have an electrically charged particle, let's say it's a proton, and it's moving. Well, that is very much akin to a current in a wire. That is, we know that it's really electrons moving down the wire, but we pretend often that it's protons moving down the wire. Well, if I have a proton moving, then I have to take the charge of the proton or electron or whatever else, times the velocity that it's moving, times B, the magnetic field, times the sine of the angle between things, and from that I can get the magnetic force. Now, please understand, the sine of the angle between what? In this first one, it's the current and the magnetic field. If the wire is lined up with the magnetic field, it feels no force. But if it's at 90 degrees, it feels as much force as it'll feel, and it works trigonometrically between that. Same thing here. If my charge is not moving, velocity, there is no force. But if it is moving at some angle to a magnetic field, the force is dependent upon the sine of that angle. Okay, in another video, I'm going to work out a couple of kind of sample problems, and that'll be all for tonight. Thanks.